You push. No, don't.
This presentation link.
Okay.
So just in case if there is an issue, you can download that and stream from YouTube.
I think it is coming now, right?
Yeah, it is coming.
Yeah, it's coming clearly.
Absolutely.
Yeah.
Can you go to
Not
the
a-
second slide?
Yeah.
Yeah, it is first slide now. So
Yeah, gone to the second slide.
okay,
Wait,
so-
let's.
Yeah.
Yeah, that slide is not changing on YouTube.
Now it's
Oh,
changed. Yeah.
Yeah, it is
fine.
coming. So there is 30 seconds lag
Now
I
what
see.
do,
Okay.
what do you see on the slide?
on
I'm
YouTube.
still on the first slide.
Wait. Its connection is excellent. You can start, Bhutan.
Good afternoon to all. It gives me immense pleasure to welcome you all on behalf of the Ocean Society of India, Pune chapter. We organize talks and scientific sessions involving eminent speakers with an aim to popularize the atmosphere and ocean sciences. Basically, we try to disseminate the knowledge in simpler words to our broad audience through these talks. So far, we have been fortunate to get generous speakers who take the pain of explaining this complex climate and earth system science in the simplest manner. Today is the third webinar in that series, and we are delighted to have Professor Ashok Karumuri as the speaker. Professor Ashok received his PhD from Andhra University in 1997 and did his postdoctoral research at the Frontier Research Center for Global Change (FRCGC) of the Japan Agency for Marine Earth Science and Technology (JAMSTEC). Later, he worked as senior research scientist and chief of the climate operations at the EPIC Climate Center, Busan, South Korea. Prior to joining the University of Hyderabad, he was a senior scientist at the Indian Institute of Tropical Meteorology, Pune. His main research areas are the Earth system modeling, monsoon variability, and climate change modeling and applications. He has extensively worked on the tropical Indo-Pacific variability and predictability. Professor Ashok has received several awards and recognitions in his outstanding career. He is an elected fellow of the National Academy of Sciences. He also served as a member of the WMO Commission of Climatology's task team on global seasonal climate update and the Indian government's UNFCCC climate change negotiation efforts in the past. He has published more than 110 peer-reviewed papers with cumulative citations of more than 10,000, which an H index of 32 and I-10 index of 58. At least 5 of the first authored papers have more than 250 citations. He was also listed in top researchers for the years 2018 and 2019 in the list that was published by the Stanford University and PLOS. With this, I invite Professor Ashok Karumuri for the talk. Sir, you may please unmute yourself and start the presentation.
Yeah, I'm unmuted, right? Can you hear me? Okay, thank you. Thank you, Dr. Bhupender, for that very kind and kind introduction. So this talk, it's basically a new paper that has come out of the PhD thesis of my former student, I should say now, Dr. Fiba Francis. This is on decadal prediction of Indian Ocean dipole. So basically, this is still early times for tropical decadal prediction, but definitely there is a signal that tropical variability can also be predicted on decadal time scale. Actually, as the moment I say this, it's sort of a paradoxical thing. We all know that, in the tropics, seasonal prediction is supposed to be better because of the ocean memory, ENSO. So you have all the processes, ocean has more memory, and so because ENSO is there, so that was the basis for seasonal prediction. On the other hand, when you come to the decadal variability, things are slightly different in the sense, you have longer variability such as Pacific decadal oscillation and there are many modes, but their signals are more in mid latitudes. And what we are talking here is basically not the prediction of decadal manifested decadal things like PDO, but we're talking of intraannual Indian Ocean dipole and intraannual ENSO. So this has been a big challenge. ENSO, you predicted so well, but unfortunately decadal models do not give you any signal. For the last few years, people have been checking that. Not much progress has been made. However, now when you talk of this is something interesting. That's why I hope many of you young people who are there, it will be an interesting thing. And the CMIP6 data has come out, and a lot of new data are coming. So whether you want to do analysis or whether you want to do your own predictions, as a researcher, a group leader, this is one opportunity. So my flow of the talk will be something like, just 1 second, Sangeeta, adi local petrol, my flow of the talk, the introduction and basic background, various temporal scales of prediction, data sets used, and the skills, potential mechanism, summary limitations and scope, and of course acknowledgements. So this paper, we also collaborated with Matt England, Professor Matt England. This work actually started way back when I was, proposed this Surprise project in CCCR when I joined then, and then that continued, and FIBA visited there in 2015 or so, and it took its own time, and it got stuck with Nature Communications. Finally, we got it published. I hope there is some interest for you people in this. All of you know the Indian summer monsoon rainfall during, this is a standard picture, most of you know. And we also know that Indian monsoon varies intra-annually, and you know that these bulbs that you see in the drought cases are El Niños, and on the top this is La Niñas, positive bulbs, blue bulbs are La Niñas. So there is a very good relationship, and we all know. We think we know at least some of the time the way through which ENSO affects. I personally believe there is still a lot we have to learn about how the ENSO affects monsoon, the mechanisms. They're not entirely separate from one another. And then in late, so ENSO is, then came the Indian Ocean dipole in 1999. It was the 1997 case, that sort of the dipole case sort of triggered any amount of curiosity, and the ENSO in that year, the 1997 El Nino was, it's the mother of our El Ninos, and people could predict it well. And so people thought there will be a big drought, and what else, in India drought, and Japan maybe, floods, and Australia drought, and so on and so forth. However, in many places the signals reversed. India enjoyed its technically IMD definition wise, it was a normal monsoon. It's just -2% below normal. And there was some surprises. Then oceanographers looked at it, and they identified this Indian Ocean dipole. And during that time, anyway, I'll come to that. So positive IOD events, most of you are know about IOD. So Indian Ocean dipole is something, this is the structure, positive phase. It's anomalous cooling in the eastern box of equatorial Indian Ocean, tropical Indian Ocean, and western box is warm anomalously. Normally what happens is it's a slave to ENSO. You have a signal in Pacific, the same signal will come here after. I think I need to take this some important call if I'm correct. Just 1 second, please. Hello, sorry. Hello. Oh, who is this? No, I think I'm sorry, wrong. This is a wrong call. Okay, so this type of structure that you see here is very, very important. Once in a while it happens. Normally it's a basin-wide mode, which follows ENSO after 2 to 3 months. So that's where the top mode is. If you do an AOF analysis, you get a basin-wide SST warming or cooling associated with El Nino signal. Okay, and sometimes El Nino signal can also give you, if you do an AOF of total Indo-Pacific mode, you will get a slight cooling here in the first mode. Okay, but most of it will be warm, not like this. So in once in a while you have Indian Ocean's its own coupled dynamics manifestation of this positive dipole with cooling, anomalous cooling in the east and anomalous warming in the west. And this modulates this is associated with the change in circulation. You have anomalous upward rising here and subsidence in the east. Okay, so this is what is called as Indian Ocean dipole, positive phase. And the opposite also sometimes occurs. It's the negative one. Obviously, here in the positive phase, you get more rainfall in the east coast of India. I mean, off the coast of Africa, and this is the structure. And this also comes with anomalous changes in the subsurface. The thermocline showers up here, and in the other side, in the west, it deepens. So this is the structure, and here too you see the opposite. And all of you know the Kelvin wave, the mechanisms, and all these things. And there is of course a connectivity between Pacific and ENSO. Through atmosphere, both of them, IODs and ENSO, connect to each other. But it doesn't mean that IOD is part and parcel of ENSO. No, there are many IOD events that are independent of ENSO. Like the recent 2019 first 2 months, May, June, there was like a Modoki-like signal. Then it died away, and you had the full-fledged one of the big IOD events. Satyavan has a nice paper. Many of you must have seen that. And global impacts are also known. Yes, and I might as well tell, if there are some students, there is something called as Nichols dipole. Much before this IOD was introduced, Nichols dipole was also introduced, but it was more of the ENSO related dipole. If you go back to see some of the old papers, Nichols dipole, you might want to see. I also referred to it in my 2003 Journal of GRL paper. Those of you who are interested can check that. Okay, so this is the mostly independent of ENSO. Okay. So some of our old analysis, if you see, when you do the coherence, wavelet coherence, there are decades when you have equatorial Indian Ocean U wind anomalies. If you take that and correlate, do the coherence with IOD, the top one, and NINO3, middle one, and the coherence between NINO3 and IODMI, you see that there are decades. Because why I take is because the equatorial Indian Ocean, this is winds are measured, they're part of your IOD coupled dynamics. So you see that they are very well tightly coupled in these decades, 1960s and 90s, when IOD was very, very strong. They were very, very nicely coupled here. Okay, and from intra-annual through quasi-decadal up to 6 years. In fact, in this paper we show that IOD has a periodicity of 5 years, but now you can go and check with the updated data. Okay, but on the other hand, El Nino coherence with the local winds is dominant in 80s when IOD winds were not so much, and the coherence between these two are relatively much lesser. Okay, at different periods. It doesn't mean that ENSO can't affect IOD or IOD can't affect ENSO. Big events will have a signature, but triggering. You have seen several papers how ENSO can trigger Shinoda and Hendon, and several papers through fluxes, through atmospheric bridge. Similarly, Osimo's papers, they talk of how IOD can be trigger an ENSO, and there is a lot of discussion. Okay, the teleconnections. I'm showing only here the paper from one of our review paper. After removing the ENSO, you can see the global teleconnections for June, July, August. And September, October, November, when the IOD cycle, IOD, after that IOD dies, as most of you know, and ENSO teleconnections, you can, all of you know, but you can refer to many of the papers. Okay, now coming to the basics of some of this temporal scales of prediction, different scales of prediction. A lot of this, some of the slides are courtesy Professor Juni Lee. But wherever I have taken the slides from her, I have put her name there. Anyway, we all know different temporal scales of prediction. Now casting, okay, within a few hours, right? Then weather prediction, 2 to 3 days. Medium range weather prediction, 7 days, maybe. There is no rigid rule. WMO may have its own definition, 7 to 8 to 10 days. And extended range prediction, what we do at IITM, up to 21 days. One of the best products Sahai's group has produced, and seasonal prediction also. We have nice work being done. All these things, India now we're doing very good predictions in weather to seasonal prediction. Again, IITM, lot of work is being done. So if you see that decadal prediction is still, it has been a challenge, not for us, not alone, particularly in the tropics. There has been a lot of discussion and controversy about decadal prediction. But anyway, that's a different thing. Then you go to climate change projections. Now, if you see the top three, now casting through medium range weather forecasting, mainly initial atmospheric value problems. SST doesn't change so fast, so you keep it, whatever you keep it, you can maintain that. But on the other hand, whatever changes are there, it's in atmosphere, stochasticity, it has to come from atmosphere, so you make multi-ensemble weather predictions, okay? Then extended range prediction, a seasonal prediction, obviously, of course, still the initial conditions are there, but it's a coupled phenomenon. So LBC driven problem, a lot of it. And extended range too, if you see some of the papers that talk of, MJO type of, many things, there is intraseasonal variability in subsurface also, and surface SSTs and all. So probably you need boundary conditions. And if you're using a land, we know that land, Saha, Subodh and all do a lot of work. Land surface is important, and how that changes in that an intra-seasonal. Shukla has been talking a lot about the importance of land use, land code, the parameterizing them and assimilating them for good prediction of intra-seasonal variability. It's a boundary layer problem too. Then decadal prediction is of course an LBC driven problem, but people call it as initial value problem because I will come to that. Then of course your climate change, all of you know, it's driven entirely by external forcings, okay. But initial conditions also to some extent matter, okay. The seamless weather prediction, that's what we talk everywhere now. So use the same model, you can predict, you go ahead, but as far as the science is concerned, again, this is the courtesy of Dr. Junili, this slide. You can see, all of you know the science of it, fronts, convective systems, cyclones at different time scales, MJO to BSISO, MISO, and all these things, NAO, monsoons, this seasonal, QBO, TBO, decadal, PDO and AMO, and century, anthropogenic force changes. Mind you, anthropogenic changes, your aerosols are a dicey thing, they can affect. We started with climate change, but their importance on weather scales in terms of stratification and seasonal scales. We have some papers with Suvarna, Fadnavis. They play a major role on different time scales also. But gases, anyway, they're slow, So seasonal, their importance is from decade to century. So this is the major modes of variability. Now physical process, again, you can get them on different time scales. Atmospheric region, what are the important things, land, you can have a look at this slide. Then the important thing is, the atmospheric chemistry also plays a role in decadal time scales. How and why? There are arguments that the skill of prediction, of decadal prediction, comes because we're in an era where anthropogenic impacts are increasing. So, you don't suddenly double your emissions overnight, but there is a particular track. So there is some sort of predictability, if you agree. So the track is there's not so much of stochasticity, and that very much drives your emission. So when you predict them in future, the aerosols give you some certain amount of control. So this gases and aerosol, this atmospheric chemistry and plays a major role. So obviously you need to have the transport and all, but that's one basis for decadal prediction. Plus this is atmosphere. This is what I said, initial conditions means I would put it in terms of atmospheric chemistry. But more important is your oceanic. We have processes. We know that Pacific Decadal Oscillation, AMO, and some of you may know my work on decadal Indian Ocean Dipole, which was motivated by Manabe since his decadal ENSO. So I will come to that again. But these are the surface process, decadal process are also very, very important. So this is what is giving you your skills on decadal prediction. It's heuristically true. You can easily understand PDO, AMO, and land surface also slowly changes. You know, your snow cover, for example, may have its own signals, the way it melts. I mean, this is all, you know, the science is evolving. Nothing is stopping you to think and check. This is such a nice virgin field. A lot of things they need to be understood. Okay. Okay. So physical base for prediction, again, it's the same thing. Initial conditions in this range and boundary conditions from seasonal to monthly. This is again intraannual variability. External forcing. I don't know what is SKI, but you know, external forcing and then natural versus anthropogenic. You can see between decadal and century, multi-decadal and century scales. Okay, so current status again, weather prediction has matured in mid latitudes, though for us it's still we are there, but we still have to mature. And intermediate to mature seasonal prediction. Again, this you have to take it from the context of global mid latitude this thing. And decadal, really, I don't know whether it's intermediate because for the tropics at least it's nascent. Okay, I don't know. I mean, yeah. Then anyway, projections, intermediate to mature. Again, depends on where you want to do that. There's a lot of other questions why they are, whether you can argue for everywhere. But this is in general that's true. You can take that. Okay, that's nice. So same slide from Boyer's similar thing paper. So initial value problem for the predictions and forced boundary value problems later. So near term decadal, you know, there is some role of initial value and there is role of your forced boundary conditions. Yeah, it's nice, isn't it? Now, these are some of my own results, slightly old, but I think it's okay. Qualitatively, results are not changed. So when we did these correlations from APCC predictions, observations NINO 3 and model NINO 3, for different seasons, at that time we had a 6-month lead prediction. So 6 months also you can see very nice 0.8, 0.9, even 1 year you get very nice correlations for N. So those of you who have studied Raghu Muttugudde and Nandini Ramesh, you know, talks of 2-year predictability from subsurface, and so you can predict. The challenge is you get that signal, but whether it becomes a Modoki or a canonical El Nino, you know, that distinction is not clear up to, you know, just it's clear up to 3 to 4 months only. But it doesn't matter, right? You have you're going to predict at least there is an El Nino. El Nino has a good signal, and El Nino Modoki is relatively challenging. But still there is good skills depending on the months that you want. You know, this is 1 to 3 months, it's 0.6, and this is 4 to 6 months, 0.7. I'm sure the skills have increased further now. And coming to our own Indian Ocean Dipole, well, unfortunately, it's a very, very poor and pathetic performance. For example, when the IOD germinates, its MAM starts Genesis, and the skills are very poor, MME skills. These are individual models. And then 1 to 3 month lead, it is some skill is there, and 4 to 6 month lead, it vanishes. And peak period SON, yeah, definitely you see some skill. 4 to 6 months, it's not much. And we have taken the total Indian Ocean Dipole Mode Index, right? West minus east, anomalous SST, west minus east, area average boxes, all of you know that. However, I mean, it has been recognized that your Indian Ocean Dipole prediction has been challenging because of various factors. Whereas, because it's connected to monsoon also, among other things. So one of the best models that gives you a good ENSO prediction is your Syntax F model, which has your Eastern IOD box. People use that, and interestingly, you know, predictability is much stronger in Eastern Indian Ocean box than IOD box, you know. And I'm sure, I mean, some of the audience who are here about IOD from CFS can comment on this if the skills are better than this. But you know, this is one of the best models you have up to 1 year, and in some cases, case by case, this is Lewis paper, Most of you must have seen that. Sorry, I should have put it as Jinjia Lewis paper. 24-month lead for the period, 18, based on syntax F. So, but on the other hand, normally the skills are rather poor. You get a skill of, depending on when you have it, May, when at 6 months lead, it's there, and you can see there is a vote of skill of 0.6. Curiously, the skill is much lesser at lead month of 3. Okay. Anyway, so you can see some of these things, and so this is the state of the Indian Ocean dipole prediction. And what is the basis for decadal prediction? There is no surprise, and lot of the work, some of those who are interested must be studying Doug Smith's work, the subsurface. The main thing, the skills, that lot of skills have been shown for mid-latitude SSTs. You can see this one from Northern Pacific. Okay, Mueller et al. 2 to 5 year hindcast skill. The temperature skills. You can see that in many of the mid-latitude oceans, and of course land also you can see. And then the tropics, the skills they're relatively poor. Okay, but still you can see some skill in Indian Ocean, but there is no skill whatsoever in Pacific. Even this picture, this gives you a hint that there is some skill in Indian Ocean actually. This paper too. But where is it about Pacific? It's much weaker. And so this is why it's weaker is a question that needs to be discerned. So and these skills are actually average skills for 2 to 5 years. Then you get a significant skill, but definitely 1 to 1 year. If you take each year, it will be much lesser. And another paper that talks of this Borchardt et al. They talk of the skills coming from this SST skills are associated with upper ocean heat content, 700 meters at lead is 1, very strong. 3 to 5 years when you average it in 7 to 5 years. So this same thing you get this reflected in the subsurface SST. This tells you that whatever signal is there in subsurface plays a major role in giving you the skills of SST. Okay, now coming to our own results here. The decadal hindcast outputs from decadal runs of CMIP 5 have been taken. The runs have both anthropogenic and natural forcings. The data sets that have been considered are CMIP, CAN-CM4, MEROC 5, BCC, CSM, GFDL. We actually analyzed Hadley Center model, but the skills were probably, they have many varieties of runs, but at least what we saw there was no skill for IOD anyway. So it was there, basic skill, but not beyond on decadal time scale. So we're focusing on these few models that we download as a part of CMIP models, actually, not independent of that. So validation with HADA assisted ORS. So then the analyzed models are, these are the models, and you can see some other initialization, full field, anomaly, full field. So there doesn't seem to be what you call as a particular scheme that helps in improving the prediction. Anyway, so we'll be focusing on CAN, CM4, and MEROC and GFDL. You can see these 4 models. You can see that. So methodology is the ensemble mean of the 10 initialization of the model output have been calculated, and the output has been divided in 10 groups, each with a time span of 51 years, depending on the time elapsed of initialization. Then you get the skills, and we also did some basic UF analysis. Let's spend a little bit of time on this one, how this, whatever I have talked here. We have taken 10 initialization, then 10 groups, and ensemble mean has been taken. For example, this 1960, you start with 1960, you make a run with 51 years, you make this run. So what you have done is, this is 1960, you start with initial condition. First year is 1961, 62. After 1 year lead, this 1 year lead, and 2 year leads, and here it's 2 years. Again, it continues like that, 51 years. Okay. Now, when you do that, what you get here is, they have done 10 simulations. You see, 61 to 70 initial conditions. So this one is 51 years. This one is 51 years. Each one 10 ensembles. So now, if you consider that, when you have done that, you have different leads. Okay. For example, you have year 1 here. Okay. all of these are year 1 leads. You have data for 51 years. All of these are year 2 leads because you start with 62, you completed 1 year, you completed 2 years. So this is year 2. And so on and so forth. You have like this year 2, year 3, year 4, you have leads up to 10 years. So ENSO prediction, these models, they're all up to 1, this is, mind you, this starts with 1 year, not 0. So after 1 year, all these things are still significant. And some of them are still significant up to 2 years. And you can say there's no surprise here. Many papers tell you that ENSO you can have a skill up to 2 years and discernible skill, usable skill up to 0.5, 0.4. Doesn't matter, whatever it is, statistically significant thing. We are doing academic work. We're not going to predict. And so the per se, but so this tells you that this is still significant. All of these are, after that the skills fall below the statistical significance after so many years. And other papers, there are papers for example, such as Gonzalez. This also indicates a similar thing. The Indian Ocean dipole, how it plays, So anomalies, correlations. Our skill set, nothing but anomaly correlation coefficient between predicted and IOD index. So out of these 2 models, you see that there are 2 models. This green Mirok model and this red color CANCM4. Very interestingly, these two are not only significant at one year lead, 0.6. This is the statistical significance, right? So they're continuing. The skill is increasing, continuous. They're more or less hovering around this significance level for almost 10 years. Some of them, this for example, it has slightly dropped down, but is still statistically significant at upon 90% significance level. Well, is it really can you translate it into real prediction? Probably no, but this gives you a hint, a flavor, whiff of this. Yes, there is decadal prediction. There is some memory. Okay, you can see that up to 8 to 10 years you can have this one. Then, okay, that's statistical significance. But normally, as a seasonal prediction specialist who is there in the group, you must be doing the persistence. You persist the same forecast, and you see persistence can be calculated in many ways. You persist the first forecast and allow that, keep that only as your prediction, and see whether your new forecast, whatever you're doing in real time, is better than that persistence, or simply give climatological value. Is your skill forecast better than climatology? Otherwise, it's of no use. When you do that, your CANCM4 and Mirok, again, the corresponding these dashed lines, the persistence for those things, they beat that. And had ISST, if you use the direct had ISST data, persistence obviously is not there. So, now before we go further, we know the IOD is associated with EVOF2 when you take the Indian Ocean SSTs, equatorial Indian Ocean SSTs, and so this is the had ISST EVOF2, and this is the ERA interim. So if you take that, these 2 models, our Mirok and CANCM4, they get a semblance of Mirok particularly gets a dipole event, okay, but CANCM4 is doing okay in terms of gradient IOD-MI, but this IOD is a bit funny, okay, but still you can say that there is some sense of it. And then if you come to BCC and CANCM4 poles are all south of your 10 degrees south. If you remember some of the papers where Namalai, he talks of the signal associated with non-IOD processes. The subtropical dipole of Behra et al. I mean, it's capturing something else. Okay, now let's compare the predicted IOD with the observations. Okay, so had ISST, the black line, and your 2 models. We took only these 2, Mirok and CANCM4, because they're persisting. Let's see. So at different leads you get the skills. You see there are the green color means both of the models are showing the phase of this IOD. Red color means at least one of the models is showing the red phase of the IOD. Yeah. So very, very interestingly, at 7-year lead, what you get is, most of the negative IOD phases are being captured in this by these 2 models. Okay. But here in the recent period, positive IOD signals are captured. Now this begs a question, is it really predicting the decadal intraannual IOD, or what we proposed, decadal Indian Ocean dipole in Ashok et al. slow process that are there. We don't know, but at least as far as the IOD phase is there, it's representing. Is it noise? We don't know. I mean, there's only 2 models. Much more work has to be done, but there is some sense that something is happening there. Some models are capturing these 2. So what is the source of prediction? So FEBA has gone and checked it in ORAS data. This is average of 300 meters to 800 meter depth from previous years. So you see that there is a positive correlation south of South Africa, and further south there is a negative correlation, and this is at different leads. This is 10 year minus 10 year, so minus 9 years. This is 10 years before an IOD occurs. You get correlations associated with the IOD in Southern Ocean, and the signal is moving east very interestingly, and it's moving. Actually, some of it is going away that side, and here we see that the signal moves coming here. At this point there is a current that goes towards tropical areas. So we check that whether there is something that is coming to tropics here. We tried to check whether the signal is coming through Pacific and Indonesian through flow. That nothing worked out, but this seemed to be the main pathway. So if you see that vertical distribution of anomaly correlation of IOD with the depth, from this 50 degrees south, 40 degrees south, and you go on, do that up to here we have seen minus 6 years. There is this connectivity. Then from minus 6 you can see at this point, oh sorry, some issue here. At this point the signal is emanating out, is coming out and swelling up at 25 degrees of the coast of Madagascar. Around the places is upwelling actually. There is a current also apparently there, so this is associated with that, and the signal is upwelling. You see the signal, and you see after minus 4 years, before this is minus 5, minus 4 years, you see the signal coming here almost in the tropical areas. So minus 4 years you get the signal in this place, okay. Then minus 3 years the signal comes here, and from here it becomes a bit dicey. This is in the subsurface of the ocean, surface to 100 meters. Generally you would expect that to come up instantaneously within a few months, but that doesn't seem to happen. It is persisting, and but an IOD seems to form. This is minus 2 and minus 1, and an IOD seems to form only after 3 to 4 years, though the signal is there. You can see the formation of dipole. Okay, you can see that. So what is basically happening? It looks like, I mean, it's very what we can at this stage conjecture that there is signal that is coming from some memory that is coming from Southern Ocean is there, that if the conditions are conducive and if there is a trigger, be it monsoons, be it ENSO-related wind changes, be it fluxes, it's waiting to be tapped. Something has to bring it out, and then IOD will form. This is the conclusion we can make it at this juncture. In fact, this type of current coming up, there is sufficient literature. Equatorward Antarctic intermediate waters enter the Indian Ocean from the mid-ocean of the southern Indian Ocean, advected with the subtropical gyre, and transits to the north to the western boundary. So this contributes about 10 to 20% of the water into the equatorial Indian Ocean. Okay, it comes to 5 degree north. Okay, so there are there are a couple of papers here, and models. That whatever we saw was ORAS 1. 10 years before, you can see some signal, similar signal in the Southern Ocean also. Widely different from one another, but there is some signal. So this is what is there. So what is the mechanism? In summary, what we understood is, there is deep water, there are a bunch of deep water that's there. It comes at 300 to 800 meters. It moves, along this way, and then it moves non-meridionally north and upwells along Somali coast, and then comes into the equatorial area, okay, and waits to be triggered. So that's the conclusion. There are two models. CAN-SIM4 and MEROC are able to predict IOD signals at long leads year by year. This multi-year predictability potentially lies in subsurface signals coming from Southern Ocean into Indian Ocean. So intriguingly, the ENSO is not even predicted. I mean, these two models predict ENSO at 1 year. Of course, forget about monsoon in these two models. They have not been so much worked on, just like our CFS or herbal models. So definitely, I mean, you can do that, but you have to understand the drivers, snow cover, what is driving monsoon decadal variability. Monsoon centennial variability we have shown in our model experiments and paleo simulations and analysis in last few papers, Charan's papers. The centennial variability also, and Supriyo's work tells you multi-decadal variability of 50 years. Supriyo incidentally is also partner in our paleo model analysis and experiments. There is that still. So, but what are that? Where is it coming from? We have to understand. But it's much probably easier to aim to predict PDO and even intraannual variability, whether there is a signature that is coming, or is it ENSO dynamics are only primarily connected to only equatorial area. There is no signal that's coming from far off, so that's why you're not getting it. These are some of the questions. As you talk, these questions are raised. A lot of gaps are there. One may even question whether the skills that we are getting is random, noise. We don't know, but definitely they're statistically significant. There seems to be a plausible mechanism. Okay, there's a tantalizing opportunity. Look at it further and make your own thing. Okay. And there are several papers that talk of impact of Southern Ocean and Southern, SAM and all to monsoons through various pathways. Wenju's papers, and I think Seelan has a recent paper. So, but what we're talking is 10-year lead. Yeah, okay. This is very, very interesting. So I hope many of the young people get intrigued by this and have their own questions and ideas. And thank the OSI Pune for giving me this opportunity to talk. Thank you very much. Yeah, and I would be happy to take any questions to the extent I can answer. Thank you.
Yeah, thank you, sir. So there are few questions in YouTube live chat box. So I will request Dr. Aditi, can you please read them out? I think you are muted. Can you unmute yourself?
Oh, sorry. Am I audible now?
Yes.
Yeah, okay. So all three questions have come from Gyanshilan sir. The first question is that Borchardt 2019 talks about the skill of 5 years average field, whether they can be translated to IOD prediction skill.
Well, this is what, Borchardt has talked about the 2 year and 5 year. When you average that, naturally the skill will increase. But taking 1 to 1 year, this is one thing we at least in our analysis we have seen that. That's why we try to do that at 1 year, each individual year leads. And yeah, I mean, depends on their model. We have seen so few models have skills only for decadal prediction of IOD. So if their model, I don't know which model they have used, but if they are used one of these two models, you should be. And somebody can take that data and analyze. Yeah.
I think you have mentioned just now in the chat box that MyRAC 5 has a good 1 year skill, and he has asked what could be the source of that, and whether MyRAC 5 skills has any signals from Pacific for its better skill in IOD prediction.
No. In fact, we checked that also. Pacific, definitely Pacific triggers and all, they may be there in cases like 1997. Okay. But definitely beyond some time, there is nothing. I mean, ENSO itself, you are unable to predict beyond 1 to 2 years in that model also. So nothing is there. We tried to do that. We tried to see if the signal is coming through Pacific, but nothing is there.
Okay, the second question is, what is the mechanism for the subsurface signals in the Southern Oscillation to reach equatorial Indian Ocean?
Southern Ocean. Yeah, FEBA has identified these two papers. Details can be there. I'm not. I don't know whether FEBA is here. She's affected by corona. I don't know whether she joined today. So this is the papers, mechanisms, and Professor Shetty was also there. Luckily with us, he's one of the co-authors. So he and there is some sort of island there where this upwelling happens, and through some geology the signal seems to come up there. So that's what Feba's interpretation is. And these two papers are also talking of similar mechanism. You can see that Yu et al. And MUC, Madagascar undercurrent, for further details for oceans. So the
So
paper
you're
has
saying island somewhere in the equatorial region or island somewhere in the
off the coast of Madagascar. See, from southern
the coast.
they're coming into Madagascar. From there, these pathways are known, well known. There are the papers. The question is why it's not coming up in the equatorial area immediately. So I think probably the signal is relatively weak. So it's waiting for some trigger. Once it is there, it's providing the basic background, the warming conducive, which can be amplified through some sort of coupling. So that's our interpretation.
Yeah, and the third question is the western boundary currents are signals from tropics to higher latitudes. How do they act in the reverse direction?
I don't know much about that, Only you have to see these papers. Feba, are you there today? If Feba is there, she can answer that. She has gone through the papers. Unfortunately, I didn't peruse this very clearly, but definitely these two papers are you can look at these two papers for a detailed mechanism. They are there in our Frontiers Climate paper, 2021, Feba et al.
One last question from Ganchilin sir only. Have you checked the PDO skill in MyRock 5?
No, we have not seen that. No. Very interestingly, one of the previous MIROCs had a very bad skill for ENSO, not ENSO, warming trend, global warming trend or something. But we looked at paleo time scales. But this model, at least for prediction mode, it seems to do quite well. Yeah.
So I have a question actually. Have you identified any models which are equally, which have either equally good prediction skill in both IOD and ENSO or equally bad at both IOD and ENSO? Because I always wonder when we say that, there's this interlink between, or there's a teleconnection between all oceans. But there's always this question, whether you get one basin to predict nicely and the other one is not doing so well. So where are we going wrong?
Yes, good question. Very nice. But that is sort of, I don't, because if you talk of basin-wide warming, that would apply more because it's completely slave to ENSO. But years like 1961, 63 and 2019, 67, even without an ENSO, you get an IOD. And there was one famous case in, if you see the Venju's papers by Venju, 2006-7, there is one more year. Out of these three, 1 year was with La Nina. Even recently, there was an IOD event with La Nina. So it is always, it may not be associated with El Nino. So you can't expect that. If something is coming like that, it's just a stochastic. I don't think there is any real physical basis. You can check for years like 1997 or Izumo talks of one IOD triggering an ENSO. Those years probably you can see case wise, but not for general hand. You can't do that.
Thank you, sir.
Okay.
Yeah.
I just wondering, Ashok, so how good this model, this like MIROC 5 will be good in value timescales with decadal resolution?
This is what I was telling in our first paper, Charan's climate dynamics. We in fact checked out MIROC. I don't know whether it's the same version.
It's not there in that
It is there. No, our analysis, we did that. Its global warming signal was very, very funny. I mean, all the other one was showing this slow type of thing, slow trend, 1,000 years. Only now the temperatures have gone up, but that was showing something like this, big trend over 1,000 years. So we chucked it out actually. We didn't use that. But this is a different one. This, I don't know whether the version is different. This assimilation in a prediction mode, the model. So assimilation seems to make a difference here.
Okay.
Yeah.
There is one more interesting comment from Dr. Gyanshilan. He is telling that from the figure, the upwelling appears to be disconnected at about 150 meters.
Mm-hmm.
Whether it raises any possible mechanisms.
Maybe we don't know. But as of now, but it's a continuous. The maximum is somewhere located, but still there is a weak signal that is coming up. So it's sort of a coherent signal that you can see that is emanating.
Yeah. Thank you so much, sir.
This one. You can see the continuity. It's there. Yeah. Yeah, there is some other mechanisms maybe there, we don't know. There is quasi-decadal variability and any other atmospheric signals. That's why I said, what we got is, this is mechanism, there is something, how much is it robust? I mean, there is any amount of opportunity to verify these things and see whether we can expand this beyond, and what is happening in Pacific is an interesting question. Yeah. Right.
I think there are no, I don't see any more questions on the YouTube live chat box.
Yeah, yeah.
So thank you very much, sir, for such an enlightening talk. It was our pleasure that you accepted our invitation and gave some important insights about the decadal predictability of IOD. Now I invite Dr. Aditi Deshpande to deliver the vote of thanks. Dr. Aditi, over to you.
Thank you, Bhupendra. So I'm here to propose a vote of thanks to everyone in this webinar, and this will be the final element of the webinar. I would like to thank Dr. Ashok Kurmuri for his insightful and very interesting talk. Being a professor and head at Hyderabad Central University, I know that
I'm not the head, a professor. Yeah.
Sorry. Professor at Hyderabad University, I'm sure you have a very busy schedule, and I thank him for taking time out of his schedule and agreeing to this talk without any hesitation and any delay. And I thank him on my personal behalf as well as on the behalf of OSI team members. And I would like to extend our sincere thanks to the Director IITM Pune and the main committee of OSI for granting the infrastructure and facilities. Our thanks are also to the audience for participating in the webinar with questions and comments. And we will be operation in the future. I would like to give the entire OSI Pune chapter organizing committee, and we meet regularly to keep motivation high and keep trying to come up with new people and interesting talks so that we keep the audience engaged. So I would like to thank all our team members and the audience once again, and thank you, Dr. Ashok. Thank you for joining us. So I will now officially end the event.
Yeah.
Thank you so much for joining us.
Yeah. Thank you, guys. Bye bye.
Thank you. Thank you. Bye.
Bye.